Hey guys, Mr. Rice again. Welcome back to my garage. One of the videos we did before and in some of the labs in class, we talked about capacitors as they related to the 555 timer chip. We were making a circuit that would flash an LED on and off. And capacitors reacted, we talked a little bit about them having a time constant, and the one thing that differentiates them from other electronic components we've used like batteries and resistors and diodes and LEDs is that they're a lot more dynamic. So the math that's associated with capacitors is more sophisticated because there's a time and frequency domain response to their behavior. So their voltage and current changes with time and depending on the circuit itself and outside things like voltage and resistance and things like that. So what I want to do is talk about something we were emphasizing, which was a time constant involved with a capacitor and resistor circuit, and that over time the capacitor would either charge or discharge depending on how much resistance was in the circuit and the value of capacitance. And we said the time constant was equal to the resistance times the capacitance in seconds, and that was one time constant. And one of the things that was a little difficult to explain without showing the math is where that time constant comes from and why I said things like one time constant in seconds is how much time it would take the capacitor to charge or discharge 37% of its original value. So either the voltage would come down 37%, or if it was charging from zero, it would be up 37% of the applied voltage. Now, why not 50% or 80% or 100%? What's with this 37%? Well, this is a little bit more advanced than the standard introduction to capacitors. So especially for you calc students, I'm going to show where that comes from, why that time constant is 37%. And then we're going to come up with a general. It's quite a beautiful equation, in fact, when you're able to use the math like this and use basic math, pre-calc, algebra 2, and calculus, and come up with a nice time domain equation that can give you the voltage at any time t for the capacitor as it's either charging or discharging. And even with more sophisticated circuits, the same process can be done. So let's get into it. I went ahead and started the first half of the derivation up here. Remember, Q is coulombs. That's the amount of charge the capacitor or anything might have. 6.24 times 10 to the 18th electrons would be 1 coulomb of charge. That's a quantity of charge, so nothing's moving yet. We define the ampere as being 1 coulomb per second. So now we have a flow rate or a time rate of these charges flowing. So each time one of these passes by a point in 1 second, we have 1 amp for a flow. Now, applying a differential calculus to that, that means that if it's coulombs per second, the instantaneous current would be dq dt, like so. And we also have another equation I'm going to add in, which is that the capacitor equation for the amount of charge that's stored in a capacitor is the capacitance value in farads times the voltage on that capacitor. So the bigger the capacitor, the more charge it can hold, or the bigger the voltage on there, the more charges that are on the plates of that capacitor, you'll have a higher Q, or more coulombs. Okay? So if Q is equal to C times V, capacitance times voltage, what we can do is differentiate both sides with respect to time. And since voltage is changing and current is definitely, Q is changing, we have dq dt is equal to C times dV dt, like so. What's interesting here is that if you look up here previous, I of t is dq dt. It's how many coulombs are flowing per second, instantaneous. So by differentiating this equation, we see that we now have an equation for I of t for a capacitor, which is C times dV dt. So another differential there. Okay, so this is a keeper. We're going to use this on our next bit of equation. We're going to go from differential calculus into integral calculus, and we're going to see how I do with that. It's been a while since I've done some integral calculus, but I think I can handle it. So again, I of t for capacitor, C dV dt, like so. And if it's positive, this would be the actual current flowing into the capacitor. If the current is flowing out, we may have to change the sign on this. and make it negative. Okay, let's get started again with the second part of analyzing the circuits and coming up with a time-based equation, time response for the capacitor and the resistor. And before we finish up with the rest of the calculus, the integral calculus portion of solving the differential equation, we need to do some actual electronics on this and some circuit analysis to be able to write that equation. So we now know that the time-based current across the capacitor is I capacitor is C dV dt. But the problem is, or actually not a problem, it actually kind of helps us out with the equation, is the fact that that's the current, the way it's derived, through the capacitor from plus to minus using conventional current flow. It's not the current coming out of the capacitor. So as I said earlier, there's actually several ways to look at this. One is as a conservation of currents with Kirchhoff's law of current, where these are parallel branches and no external current is coming in or out of those branches. Therefore, the two currents must add up to zero. With no current coming in or out, there can't be any additional current but zero in there. So whatever the capacitor is giving up is what the resistor is receiving. The capacitor is supplying current, the current's flowing through the resistor. So another way of looking at it from a practical sense is as the current goes out of the capacitor, what it loses in current, the resistor gains. So we could write that like so. The current loss from the capacitor is negative C dV dt is equal to what Ohm's law would say. Remember, it's a linear device, so very unsophisticated as far as the current computation. Just Ohm's law, remember, is I is equal to V divided by R. Call this V. Same voltage here, just like a parallel circuit. Whatever voltage is on the capacitor here, it's on the top of the resistor here like so. So V divided by R. So this is the current coming out of the capacitor, the negative side. The opposite of the current going through the capacitor, and the current going through the resistor, positive sign V divided by R like so. What I'm going to do now is separate the differentials so I can use the integral to solve this differential equation. So I'm going to separate, I'm going to keep the dV on this side, negative C dV is equal to V over R dt, like so. I'm going to rearrange the constants. Capacitance value doesn't change in farads. What's changing is time and the voltage and the current are changing. Capacitance isn't changing. The initial voltage is not changing. The resistance is not changing. So those are constants. I'm going to bring the V down to this side. We're going to integrate that. And the C is going to go over to this side. We're going to have, I'm also going to bring the negative sign. So we're going to have 1 over V dV is equal to negative 1 over RC dt. Okay? Multiply by R, I'm sorry, divide by C, divide by negative 1, so the C goes downstairs on this side. We also divided by V on both sides, so this V is gone, and the 1 over V stays on this side. Now we're going to use the integral process, integrate both sides, like so. We can leave all that on the outside. Those are all constants, the negative, the 1 over RC on the outside. The integral of 1 over V dV, the indefinite integral, is equal to minus 1 over RC. That looks familiar. Talked about that being a time constant. Resistance times capacitance. Times the integral of dt. So this will be natural log of V is equal to negative T over RC. We just have a dt, and we integrate that. What we get is the variable t. The RC on the bottom like so. Now what I'm going to do is raise both sides with base E, like this. Let me start with another color. I'm going to say E to the ln V is equal to E to the minus t over RC. And I think we had indefinite integrals, so we better have a constant like so, and that constant's going to live in the exponent of e on this side. Okay? So we have e to the ln v is equal to e to the negative t over rc plus k. I'm going to do some erasing. I'm going to go right back up here. Let's get rid of all of this. So at this point we have v. This is v of t. E to the minus t over rc plus constant k, like so. Okay? I'm going to erase that last step. This constant up in the exponent, since we're adding a couple of exponents, like so, this would be the same as, this would be a little pre-calc or even algebra 2, maybe even algebra 1. E to the minus t over rc times e to the k, constant. Right? Multiply the same base. It's like combining common base and adding the exponent. So I'm just doing it in reverse. So I'm breaking this back down the reverse way. It's e to the minus t over rc times e to the k. As it turns out, e to the k is still just a constant because e is a constant. So we can change this to some constant a or c or something like that. Well, we already have c's around here. Why don't we call this, if time is 0, e to the 0 is 1, then the voltage would start out as the initial voltage, V or VO, V initial or VI for initial. In this case, because we have I's for currents, let's call it VO. So why don't we call this constant V of t is equal to e to the minus t over rc V0, some constant, some new constant A, amplitude or something like that. So in this case, we can just bring this out front because it looks a little goofy like this. So V of t, capacitor, e to the minus t over rc, whoops, put the constant first, VO e to the minus t rc. This is the decay, e to the minus something. Tends to decay slowly over time. Time constant's here. Notice one time constant, RC, at this amount of seconds, R times C, substituted in for T. Remember, T is the variable. This is in terms of T. We get e to the minus 1, which is 1 over e, and that's 2.7 something. So 1 over that is like 0.37. So that's why at one time constant, R times C, capacitor is discharged down about 37%. That shows it right there. Again, that's the tau, time constant R times C, resistance times capacitance. That's the time it takes for the capacitor to discharge 37% or increase 37%. About 5 of those time constants and it gets virtually to 0. So again, that's where it comes from, because at one time constant in time, you have RC over minus RC over RC, which would be e to the minus 1, which is 1 over e to the 1 times this, which again is about 0.37. Just like that.